tower. Now you said part B? Both of them. Okay. All right. Because really, if once you have part A, then part B I think is pretty easy, right? But without part A, I don't think you can get part B. So they want the equation of this line right here. So any thoughts? I mean, after reading it and so forth, does this remind you of anything?
Yeah, for Shanghai.
It is the Shanghai, right? It is the Shanghai problem, exactly. It is a situation where we haven't done this one already, have we? Okay. So it's a situation where we do not know this point, where the line is tangent. So we probably need to know some other point, right? And there is one other one we know, and that's what? This point right here. What is that point? 0, 1, 16, right? Because the top of the parabola, here's the parabola equation. So if you put a 0 into that, you get 100. So you know that that's 100. And the tower is 16 tall on top of the hill. So that point is 116. Okay, so once you know that, it's a pretty, I mean, it's funny to call it Shanghai Basics, I guess, at this point. But we have done a few, right? We've done a few, so hopefully that's getting easier. So to work Shanghai is what? Two ways to do slope. One is derivative of the curve, right? So the derivative of this. Now, if it were me writing this equation, I probably would write it out as 100 minus 1/400 x squared. I always think that's just easier to do the derivative so that I don't get confused and want to do a quotient rule here, because that would be a mistake. You could do it, but it would just be a lot harder than it needs to be. You're just better off writing it this way. So the derivative, the 100 to disappear, bring the 2 down in front to be 2/400, which would be 1/200 negative x. So there's your derivative. And then what's the other thing you do with Shanghai? The actual slope between the 2 points. So y minus 116 over x minus 0. And then that has to equal the derivative, negative 1/200 x. Now one problem is we got 2 variables there. We got an x and a y. What can we put in place of the y? This equation right here, right? So now is this a calculator or no calculator? No calculator. So that makes it a little more interesting. So we got 100. So in place of the y, I'm going to put 100 minus 1/400 x squared, and then minus 116. And then that's going to be all over x. And then over here, we're going to have negative 1/200 x. Okay? And so now we've got to solve that. So, suggestions? Multiply the x over to this side. So that would make that squared. Now this would be gone. Any ideas now? Add this over to that side and put the 100 minus 116 together. That'd be negative 16. And then over here, add 1/400. So that'd be 1/400 x squared minus 1/200 x squared. That's nice. They're like terms, so I can put that together. So I got negative 16 equals, what would this be over here? That's 1 minus. So it would be negative 1. This would be 2/400s, right? So 1 minus 2, that'd be negative 1/400 x squared. So we'd multiply the 400 over to here. 4 times 16 is 64. Both negatives are canceled. So that's 6,400 equals x squared, right? 4 times 16 is 64. 2 zeros. What's the square root of 6,400? Now, plus or minus, but that just means that would just be the other That'd be, if you had a line over here, would be the negative, so we can ignore the negative. So that is, what did we just find? Oh, this right here, right? So we now have found that this point is 80, and then it'd be nice to know the y value. How would you get that? Plug it into the y, so 80 squared is 6,400, so this would be 100 minus 1/400 times 6,400. So the zeros would cancel. 64 divided by 4 is 16. 100 minus 16, 84. So this would be the point 80, 84. Okay, now what? Sometimes it's nice to step back and think about what you're supposed to be doing here. We want the equation of this line right here. So what do we need to do that? Point and the slope, right? Now, to be honest, the easiest lines of all are when you know the y-intercept, right? Plus b, y equals m. But I would just do y equals mx plus b here. It'd be easier. We know the y-intercept is 116, so all we need is slope. So where do you want to go to get the slope? We got slope all over that page. Where do you want to go to get the slope? Here? What about here? That'd be faster. I mean, I don't care. It doesn't matter, but that's pretty easy right there, right? What would we put in there for x? 80. So negative 1/200 times 80. Cancel the 0. 8 over 20. 4 over 10. 2 over 5. Negative. So negative 2/5 x plus 116. Right. I mean, I hope if that's on there on Monday, we can do that. Right? I mean, it's, like I said, at this point, it's almost the basic Shanghai, right? Like with point, you got another point you should know. Do the slope between 2 points, do the derivative, you set them equal, you solve, the numbers all work out pretty nice. You write the equation of that line, okay? Oh, it's not 116. Yeah, it is 116, right? Once you have that, it should be pretty easy. From the top of the tower, the ground between P and Q is blocked by the hill and cannot be seen. What's the distance between P and Q? Well, if you're going to find that distance, what do you need to know? What those points are, the x-coordinates, right? So how could you get the x-coordinate of P? Set the y equation equal to 0, right? The parabola, right? Not y prime, but the y equation, right? Set the y equation equal to 0, the parabola equation. Well, that's this one right here. Okay, set this equal to 0. So I'd add that over there. I'd have 100 equals 1/400 x squared. Multiply by 400. That'd be 4 with 4 zeros. What's the square root of 4 with 4 zeros? 2 with 2 zeros, right? Square root of 100 is 10. You got 2 zeros, you do the square root, you get 1 0. You get even number of zeros, right? You can do the square root. So x is 200. Okay, so that's right. A lot of arithmetic here, really. If that's throwing us off, that's unfortunate. But you know, a lot of just algebra and arithmetic here. Really, the only calculus we did was a derivative, which I hope was a pretty easy derivative. And really, everything else is just solving equations and, right? I mean, really, a lot of algebra. And then what about this one? What do we do with that? How do we get that? Put the line equation equal to 0, right? When does a line equation have a y value of 0? So negative 2/5 x, subtract the 116 over. The negatives are going to cancel. So x would equal 116 times 5 over 2. So divide the 2 into there, that'd be 58, I think. 58 times 5. 50 times 5 is 250. 8 times 5 is 40. 250 plus 40 is 290. So the distance between P and Q is 90.
Wait, you plug that into what equation?
the line equation. We want to know this point right here, it's on the line. So we want to know when the line has a y value of 0.
Right.
So I put a 0 into the line equation, which is what we found in part A. And then I just solved. So there's 90 feet in between. Right? So, I mean, I hope it feels a little bit like that's, I mean, when we first saw the Shanghai problem, it was like, oh my God, I never would have thought that, right? And that's the point on these packets is we see these problems and we see them and we use them and can we see every possible type of problem? No, you know, but we can sure try. We can see a lot of them. And when we see them again, and hopefully you've tried this and spent some time thinking about it. Some of you maybe just had a blank piece of paper, you read it once and haven't even thought about it since, and now you just copied what I did, and the next time you see it, it's probably not going to be that much clearer. Maybe a little bit, but if you've tried it, you thought about it, you did some things, and now we did it, and then you see it again, right? I mean, that's how these things happen. You know, I mean, that's how you get the hang of these things. As things get more difficult, you get into college, you take these classes, things are not quite as easy as they are in high school always, right? And you have to think about it more and spend more time with it and see them multiple times, right? Okay. Anything else? Sample 1. Or sample 2. At the end of today, towards the end of the period, I'm going to give you a little hint on the pipe problem on the take. Maybe you need it, maybe you don't need it, whatever, but I'll give you just a little bit. We'll discuss it just a little bit. But other than that, I'm not probably going to really give you much help, right? It's kind of a quiz. You can help each other. You can work together, talk things through with each other. Remember, that's due tomorrow at the beginning of class. If you're going to be gone tomorrow, anybody that knows they're going to be gone tomorrow? Okay. Tomorrow? You'll be back at lunch. Okay, that's fine. Otherwise, make sure you get it to me, right? Before, so, you know, I usually say if you wake up sick in the morning, you're not going to be here, you know, you probably call somebody, have them come to your house, get it, bring it, and get it handed in, right? To have your mom drop it off at the main office or something, right? Somehow let me know, because that's kind of a due date. Most things we have is a due date. So, you know, unless you're bleeding from the eyes in the emergency room and your mother doesn't want to leave to come hand in, you know, take them. Maybe then. Maybe, no promises. Maybe there won't be a late deduction. So, okay. All right. And I'm only partially joking. Make sure it gets to me tomorrow, all right, at the beginning of class. Okay. Or Macy, you can bring it to me at lunch as soon as you get back. All right. So, and nothing else? Nothing else here? Okay. Tomorrow we're going to be talking about our quiz Wednesday, that no calculator quiz, but we're going to have a fair amount of packet work time actually in class tomorrow. So what's that?
What's fair?
What's what? What?
Fair, not
fair. Oh yeah, well, that's a good question. 45 minutes for sure, I would think. Okay. All right. Let's go ahead and talk about our theorems. Let's go ahead and get your notes out because we really didn't have any other homework. And then if you were gone, if you didn't get a chance to see the video from Friday, you know, if you had some questions on that 4.8 homework with the two theorems, right? The extreme value theorem. And so let's just go back over those two theorems real quick, and then we're going to write our third theorem. We're going to talk about it a little bit, do a couple of problems with it that you might be asked to do, kind of things you might be asked to do with this new theorem, and then work time today. To be honest with you, I mean, so I'm going to give you some work time today to do because you're going to have a book assignment. So My hope is kind of like we did on Thursday. You had time in class to pretty much get the book assignment done, so that way you could think about the packet, or tonight if you want to be working on the take-home, you don't have to be working on your book homework. Okay, so that would be kind of the goal today, is to be working on that during class. All right. So the extreme value theorem, extreme value makes you think max or min. So let f be continuous on a closed interval AB, then f has both a max and a min value somewhere in AB. Now the importance of the first two theorems is they have to do with continuous functions. That's the thing. The title of the section in the book is Why Continuity Matters. So if you know a function's continuous, like polynomials, that's why we do so much work with polynomials, because they're so nice. They're just smooth and no gaps or breaks or nothing weird going on. And so we use those a lot as early examples when we do derivatives and we do stuff like that, because they just are so nice. So if you know a function is continuous and you have a closed interval, then you know there's both a max and a min value. Okay? If you don't have a continuous function, then you might still have a max and a min. You might have one, not the other. You might not have any, whatever. This doesn't really guarantee you anything, like the card promise. If the first part's not true, who knows? Okay, but if the first part is true, then guaranteed. All right, intermediate value theorem. Let f be continuous on the closed interval AB, and let k be any number between f of A and f of B. Very important. Those are the endpoints, the y values of the endpoints, not the max and the min, but the endpoints. So this says, so any number in between there. So this says if you have that, then there's going to be some x value in between there, call it c, that has the y value that equals k. In other words, it's going to hit all the y values. That function is going to hit all the y values between f of A and f of B. If you're going to state this theorem, it's good to write it this way. But as far as understanding the theorem, think of it as it's going to hit all the values in between f of A and f of B. Between the endpoints, it's going to hit all the y values. If the function is not continuous, it might not be. It might jump. It might skip some. Okay? But if it is continuous, it's got to hit them all. All right, here's the new one. Here's the new one right here. The mean value theorem. Now, as far as theory goes, probably the most important theorem in calculus. Okay? Most important result of things we do. Now, of course, definition-wise, our definition derivatives are really important, and the limits and that whole thing. And we're going to have another definition. We're going to have something called the fundamental theorem of calculus. That's really important. I mean, let's even think of the name, the fundamental theorem of calculus. Sounds like a big deal. Okay? But as far as useful for doing things, the mean value theorem is pretty important. We're going to do one of those, show you an example. So it says, suppose f is continuous on the closed interval AB and differentiable on the open interval AB. Let's just talk about that part a minute. That's the if part. If you get an A, then your parents will buy you a car. If you get an A, right? So the title of this section is Why Differentiability Matters. Okay, so we take it one step further. So continuous means no breaks or anything like that. Now, one of the things I often will put up here is, okay, so continuous, just so we understand. And, whether you write this down or not, I don't care, but this is continuous, right? But that is also continuous, right? Both of those are continuous. But only one of those is differentiable, right? And which one is that? That one, right? Differentiable adds an additional component to it, that is, the derivative exists everywhere. So not only can there be no breaks, because as soon as you have a break or a gap or a hole, then all of a sudden the derivative may not exist. Okay? And so there's something we say, there's a term that we often hear, differentiability. Implies continuity. Now these two things don't have anything to do with the mean value theorem other than it has to do with the word differential, right? So it's a little bit of a side trip here before we finish the mean value theorem. But differentiability implies continuity means, what's that mean? If the function's differentiable, then you also know it's continuous. If you have a square, then you also have a rectangle, right? But it doesn't work the other way around. If you have a rectangle, it might not be a square, right? If a function's continuous, it might not be differentiable, like that one. But if a function's differentiable, then you know it's continuous. You don't have to say both. Now you say, well, how come our theorem says both? Well, we're going to talk about that. It has to do with the interval, okay? So if a function's differentiable, you automatically know it's continuous. No holes, no breaks, no gaps, and it's smooth. The word that we often use with differentiable is smooth, okay? Because what happens here, the reason the derivative is undefined is there's sudden change of slope, okay? We're on a smooth graph, there's not. It goes through all the different slope values. So therefore, if you were to graph, and here's another thing that is often said, a differentiable function, f prime will be continuous. So if you graph f prime, it's going to hit all those y values because the slope is just changing and going through all the different ones. Here you got these sudden changes. When you have a sharp point, you have a sudden change. So if you graph the slopes, the slopes might be down here and then all of a sudden jump up to here, right? So if you have a graph like this, it might be continuous, but its derivative graph would not be continuous, right? So those are some of the things you sometimes hear. Okay, talking about the word continuous and differential. All right, back to this. So here's the last part. Then we're going to talk about that first part some more. But so if a function is continuous on the closed interval and differentiable on the open interval, then there exists a number c on the open interval AB, for which, or such that, it could say either way there, f prime of c equals f of b minus f of a over b minus a. So just write that down. So this theorem we actually might do a little bit of a calculation. You might have some homework where you have to do a little bit of a calculation. I told you the quiz Wednesday is a no calculator. That's because there's not very much in the way of doing calculations on this quiz that we have on Wednesday. On Wednesday. Did I say Wednesday?
Is it on Wednesday?
It's on Wednesday. No, it's going to be on Wednesday. It was always going to be on Wednesday. The no calculator quiz, I think. I don't know. We got so many things coming up, it's hard to keep track, right? Yeah, Wednesday, the midterm Friday and Monday. Right? The no calculator quiz is Wednesday. All right. Anyway, not much in the way of calculations where you need a calculator, but there might be a little bit here. Okay, so first let's talk about this first part. So we just got in saying if you say a function is differentiable, you automatically know it's continuous, so you have to say both. Well, the difference is we want the function to be continuous on the closed interval. So that means that includes the endpoints. So we have to have no breaks or gaps or anything like that, and no holes. So at the endpoint, you can't have a hole, okay? Because if you had a hole at the endpoint, then you wouldn't have the f of b or f of a here. There'd be no y value, right? So there can't be any holes or breaks or anything anywhere, even the endpoint. But for the theorem to work, the function only needs to be differentiable between a and b. In other words, the derivative has to be smooth everywhere in between. At the endpoint, it could be smooth or not be smooth. I mean, we might get a sharp point at the endpoint, and we wouldn't care about that. That's why. Okay, that's why these two are said differently here. We need the function to be continuous all the way through, including the endpoints, but we only need the function to be differentiable between a and b, not at the endpoints. Okay? So that's why there's that. And so there exists some number c on AB, so in other words, c can't be one of the endpoints. It's got to be between. Okay? For which this is true. Now let's talk about this. What does that say? What's the left side say? I mean, I know it says f prime of c, but what does the left side say? The slope at point C. Right? And what does this side say? No, that's what this side says. The right side says what? Slope what? Between, which are the endpoints, the slope between the endpoints, right? So this says the slope at some point in between the endpoints, and this says the slope between the endpoints, and then they got to be equal. So what this is saying is that if a function is continuous all the way through and it's differentiable all the way, wouldn't have to be difference of the endpoints, but usually is. Whatever. So basically if a curve's nice and smooth, then there has to be some point in between where the slope at that point is the same as the slope between the endpoints. So here's how I usually draw this. If I've got a curve that's nice and smooth, like so, here's the slope between the endpoints. So if this curve goes up and wanders around and goes up here and then comes back down and goes here, what happens? The slope's getting steeper, then it's getting less steep, and then it's getting steeper again, and whatever. Doesn't there have to be some place in between here? And this curve looks like there's actually a couple. Doesn't it make sense that there would be a couple, but it doesn't make sense that there would be at least one place. If you start here and end here, the slope between them is this. There's got to be somewhere in between there that have that same slope. That's the typical picture you see for the mean value thing. Think of it this way. If I drive from here on Highway 30 to Grand Island, and I average 60 miles an hour, what would this be saying? At some point in time, you had to be going 60 miles an hour. Does that make sense? If you average 60 miles an hour between here and here, at some point, now in your book they have this problem. They have this problem about the toll booth thing. We ever talked about that? Why does it sound like, does it feel like we've talked about it? Maybe because I've been teaching this for like ever. I've talked about it every year, maybe that's why. They have this problem about, everybody been on a highway like down in Kansas, they have a lot of where you got to go through a toll booth and so you get on the interstate and you have to go through a toll booth and they give you a ticket. And on the ticket it's punched where you just got on, like what ends, right? And then anywhere then you get off, you go through another toll booth. And then they take your ticket and then you have to pay. And it's a way that they keep taxes down. It's a user fee, basically. So they take that money to help pay for the roads. And they figure this way the people who are actually using the roads are helping to pay to keep up with it. It's a toll. So they have like a story problem in there. And they say, and it says, okay, they got on at this one place. And they went down the road 80 miles. So they drove on the freeway, so they got their card, and it was stamped where they got on and at what time. It's a computerized thing, so it has a time and where they were. And they go to 80 miles down the road, and you get off, and you hand them your ticket, and they put it in the computer to read it, and then they then they tell you how much you owe, and then in the problem it says, and they handed them a speeding ticket at the same time. Right? Well, in the problem it says on the timestamp, when they went through, they go 80 miles down the road, they had the thing, and it took them an hour to get there. So they'd gotten there in an hour, right? So they charge them what it charged for the 80 miles, and they gave them a speeding ticket because what? They knew at some point, right, according to the mean value theorem, if you averaged 80 miles an hour, at some point in time, you had to have been going 80, right? Probably faster, but, at some point in time, you had to be going 80. But that's what this is saying. That's what the mean value theorem says. Okay?
Should they actually do that?
I don't know. I've never heard of that happen. So I don't know. But yeah, whenever I think of that problem, I laugh because I always think when I drive through those things, I think, what an awful job. I mean, I guess as a college student making some money whenever you're sitting in this little booth, and people come by and you hand them a ticket and you collect their fee, whatever. But God, that'd be awful. And so I'm imagining this person in there saying, well, according to the mean value theorem, this minimum wage worker who's sitting in there. But anyway, so I do not know if that's an actual thing, if they give you speed. We don't have much of that in Nebraska, though, but down in Kansas they do. I know I run into those. So. All right. So what would some problems look? Why is this such a big deal? It seems like just kind of this obvious kind of thing. What's the big deal about it? Here's the big deal about it. Because it gives us an equation that connects F with F prime. If you think about the chart, all that stuff in the chart, that's what that was. Connections between F prime and F. And when we find a maximum, a local maximum min, an optimization problems, those are all about, right, what F prime tells us about F. We try to find the max value of F. We look where F prime is 0, right? Those things are, those connections between F and F prime are really the foundation of most stuff we've done so far this year. This is an equation that actually connects those. So here's one, whoops. So first of all, let's just do a kind of a simple problem here. Okay, so you might want to write this down. This would be a typical, this probably be in your homework, something like this. On the quiz on Wednesday, it could be something like this, right? Obviously, you're going to have to state the theorem, but there could be something like this here. And this is just a pretty straightforward, okay? Here's a function. It's a polynomial, so it's clearly differentiable and continuous. It's nice and smooth. It meets all the requirements of the mean value theorem. We've got our closed interval 1 to 4. Oh, by the way, back to that open interval, closed interval thing. Here's the point. Here's why we don't care if it's differentiable at the endpoint. Because what if this graph then shot off this way? Would that affect this problem? The fact that the derivative didn't exist at the endpoint? It wouldn't matter, right? But we need it to be continuous because we need a y value at the endpoint. So we got to have those be closed circles. They can't be open circles. But we only need the derivative exist in between there. We don't need the derivative to exist at that endpoint. So that's why we have to say both parts. Okay? All right. But if you had a sharp point in between the endpoints, let's say you had the V graph, and let's say right there the slope is 0, right? Is there a point somewhere in between there that has a slope of 0? Is there any place in there that has a slope of 0? Down here, what's the slope? Undefined. So the mean, right? Or what if the graph looked like this? What if it was a V graph that went like this? Okay, here's the slope between the endpoints. Is there any point in between there that has that slope? No. See? So that's why it has to be differentiable. That's why it's got to be smooth in between. The derivative has to exist everywhere. Because here, it would fall apart, right? The conclusion would not hold. Well, that's okay. The conclusion shouldn't have to hold there because the initial part was not true. Okay? So, all right, mean value theorem. That's why you have to have this initial part be true. Okay, so here's just kind of a basic mean value theorem problem. Find the value of C that satisfies the mean value theorem. So what do you think we would do? Here's the mean value theorem. Again, it's important to remember this. This is the only one of those theorems where you actually have kind of a formula to use. Right? There's the mean value theorem right there, the conclusion. So what do you think you would do? Come on now.
Select a point.
What? Do what?
Select a point.
What do you mean select a point? I'm not sure what you mean by that.
Choose a point between 1 and 4.
I don't think we're going to choose a point between 1 and 4. We're going to find a point between 1 and 4.
This is like equal to 0.
No. We're going to need the derivative. And we need to find the slope between the endpoints. Okay, so let's go back to this. There's got to be some point, that's the point C. There's got to be some point in between here that has the same slope as the slope between the endpoints. So you better know the slope between the endpoints, right? So the first thing we should do is just plug in a 1 and a 4 over here. You really don't need this formula. If you understand what the thing's saying, you don't need to write down that formula. You just say, oh, okay, I need to know the slope between the endpoints. So I need to know f of 4. And that would be 4 cubed is 64 minus 8. That'd be 56. Plus 1, that'd be 57. And f of 1, what's f of 1? 1 minus 2 is negative 1 plus 1, that's 0. So the slope between the endpoints would be 57 divided by 3, which would be 19. So the slope between the endpoints is 19. So there's got to be some point between 1 and 4 where the slope would be 19, right? So how would I find that point? Take the derivative and set that equal to 19. Because the derivative is the slope at any point. So we need the slope between the endpoints. In this case, it's 19. And then we would find where, at what point, had that slope. Plus or minus square root of 7, would that be my final answer? No. Why not? Because we don't want the negative. That's not in the interval 1 to 4. Very good. Do not put plus or minus square root of 7 on there, or you would be wrong. Okay? And if this interval was from -4 to -1, then we would actually want the -1 and not the positive. Okay? Square root of 7. Now, maybe I should label that C. Might be better in the end. At the end, when I give my final answer, might be better to label that C. But that, it is an X value. That is where the slope would equal the slope between the endpoints. Again, slope between the endpoints is easy. It's just slope. It's just out, right? Subtract the y's, subtract the x's. They give you the input. So you just plug those in, find your y values, do your slope, and then set the derivative equal to that. Not 0, right? We're not doing the derivative equals 0. That's what we're saying, right? Look at my picture. Derivative doesn't equal 0 there. The derivative equals the slope between the endpoints. Okay, so that's just a straightforward using the formula to find it. So you'll have a little bit in your homework for that. Okay, now let's do this. Okay, might have to do something similar, or probably not from scratch, but be able to answer some questions about what we're going to do here. Like I might show you this. We're going to prove this. This is going to, that's actually the directions on this problem is prove this right here. Okay, well, we're going to use a mean value theorem to prove this. When in college, you may take, your calculus class may get into some theory a little more than we do. We don't do a lot of the theory. Take higher level math classes, they get into theory more. But this is a basic thing from the chart. Right? Just put that in your own words. What is that from the chart? Bingo, right? That's all that's saying, which we've done that forever, right? When we first learned about connections between f and f prime, it was one of our very first ones, right? But the second one, right? First one was f prime is 0. But this was the next one. If f prime is positive, then f is increasing, right? So that's something we've used from day one. Now, we just did it from a common sense perspective, right? We didn't prove it, but that's what we're going to do right now. We're going to prove that that's actually true. So if f prime, now, what I should have put here first, though, is f is differentiable, right? Probably should have said up here, assume that f is a differentiable function, right? Everywhere. So if it's differentiable everywhere, then it meets what we need. Now, again, don't get confused. Don't overthink this open, closed interval thing, right? If I say it's differentiable everywhere, which means it would be differentiable at the endpoints also, is that okay? Even though this says open interval, is it okay if it's differentiable at the endpoints too? It's just like extra good, right? If you get an A, then I'll buy you a car. And you come home and you give your parents a report card and it's an A+. Sorry. Don't get it, right? I said A. I said you got to get an A. You didn't. You got an A+. You don't get the car, right? They wouldn't do that, right? That's just extra. You got the A, and then you got this extra too, which is fun, right? Well, that's what would be going on here, okay? So, differentiable everywhere. So this will apply. This will be fun, okay? All right. It's just that we only need it to be differentiable in between. We don't need it to be differentiable at the endpoints, but if it is, fun. All right. So, let's show that, so assume it's differentiable and f prime is positive for any values in A and B, okay, including the inputs. All right, well, what we're going to do is we're going to write down the mean value theorem. So this is what a good looking proof would look like. We'd say, according to the MVT, f prime of C this right there, the C is in that open interval A B. F prime of C is equal to f of B minus f of A over B minus A, right? According to the mean value theorem, we know this to be a true statement. Okay? So now, let's multiply both sides by B minus A. So because we know this is a differentiable function, we know that this is a true statement, this equation right here. Why would we want to use that? Because we're trying to connect f prime with f, and that's what this equation does. So we're going to multiply both sides by B minus A. Now, what do I know about f prime of C?
It's positive.
We know that f prime of C is positive, right? Because that was in the if statement of the thing we're trying to prove. They told us that f prime is positive for all x in that interval. So C is some point in that interval, so therefore we know that is positive. What do we know about B minus A? Here's our interval. Doesn't that have to be positive? Doesn't B have to be bigger than A? Right? Your interval goes from A to B. Right? That's the only way you write an interval like this. Right? B's got to be bigger than A. So B minus A's got to be positive. So therefore, these three little dots in a triangle mean therefore. Therefore, f of B minus f of A has to be what? This side has to be positive, which means greater than 0. Correct? F of B minus f of A has to be greater than 0. Add f of A to both sides. Oops. Doesn't f of B have to be greater than f of A? And again, I probably could have had other, let A and B be any, A is always less than B, and for any points, any interval, A, B is any closed interval on this function. So pick any interval, no matter how big or how small. If f prime is positive, then the y value on the right has to be bigger than the y value on the left. All the time. Because A and B is any interval on this thing. So that means any point to the right, the y value has to be bigger than the y value to the left. Well, what's that mean the function's doing? Increasing. I mean, that's the definition. If you look up the definition of increasing, it means every time you go over to the right, no matter how far, the y value goes up. Right? That's what increasing means. That f of B would always be greater than f of A. Any point to the right, the y value would always be bigger than a point to the left. So therefore, f is increasing. Pretty simple little proof, quite honestly, once you got that. Once we set up the mean value thing, right? If the derivative is positive, we know B minus A is positive, then this has to be positive, which means f of B must be greater than f of A, which means f is increasing. Okay? So, classes are heavy with theory kind of stuff, do a lot of that kind of thing. Think back to geometry, the proofs you used to do, right? That's kind of what that would be like. Kind of like a proof. Okay? All right. But that's kind of what's important about the mean value theorem. It can be used in all that stuff we did in the chart. We could use the mean value theorem to prove all of that is true. Okay? All right, so you're going to have some homework questions here on your assignment sheet. It says 4.9. So we're going to do that for tomorrow. Probably, I forgot, I talked about all the different grades we'll have. We'll probably have a a small homework grade too, because I've been taking some homework at grade assignments. So I'll probably come around tomorrow and check this. So you want to get this done. So on your assignment sheet it says that. So you can work on that. Here's the third packet. If you never grabbed one of those and you want to be working in that a little bit, you can. You know, I'm going to talk about the pipe problem at the end. I really want you to work on your 4.9 homework right now. Okay? Not the take home, because it really is supposed to be take home. But you work on 4.9, get that done, because I don't think it's going to take real long. And then you want to work on the take home a little bit after that. You know, that's okay.